Guys, welcome to this new video. So this is going to be a rigid body mechanics question from the May 23 time zone 2 paper 3. So here we're told that a student models a rotating dancer using a system that has this vertical cylinder and these two spheres. And then we are told that it starts from rest and it rotates about this vertical axis. And yes, so initially the spheres are this close. And then we have this force diagram showing what forces act on it and what their distance is from the axis. And we are told that air resistance is negligible. And we first need to show that the net torque on the system about the central axis is approximately 30 Newton meters. So we know the formula that torque is just the force times the distance times the sine of the angle, but here we're not going to have to worry about the angles, as the distance, this d in the formula, is usually just the distance, the perpendicular distance. So like if we have the force over here and our axis, we need to draw a straight line that is perpendicular to our force to the axis, and this will be our distance. So luckily here we see in both cases that we have no angle here, as they are parallel with each other. So we can simply multiply with the force. We can simply multiply the forces and the distances in both cases for both forces. And the question is just now, do we need to add them or subtract them, or what do we need to do with them? Well, for this there are two main sign conventions. One of them is that any force that rotates something about an axis in the clockwise direction is considered to be negative, and the force that would rotate something about an axis in the anti-clockwise direction would be positive. And then there's also the opposite of this. It's not really important here which one you use, it's just important to be consistent. So let's just say that clockwise rotation, so rotation like this, is positive torque. Let's just assume that. So we see this is in the middle, our axis, so everything is going to rotate about this point. And if we look at this 50 Newton force, we see that it would push the whole thing this way, which is clockwise. So this will have a positive torque, and same with this 40 Newton. It would make the thing rotate this way, which is also clockwise. So they both have positive torques, so we need to add them up. But if like the 40 Newton force would be this way, then this would be an anti-clockwise rotation, and so that would have to be negative. But here we simply need to add them up. So the arm of the 50 Newton force was 0.5 meters, and the other one was just 40 times 0.2 meters. This will give us 33 Newton meters. So that is the net torque, which is approximately 30. Then we are told that it rotates from rest and reaches a maximum angular speed of 20 radians per second in 5 seconds. We need to calculate the angular acceleration. And well, is pretty much the same as we would have in normal mechanics. We know that acceleration is the change in velocity over change in time. And we have almost the same formula for this rigid body mechanics, where we have that the angular acceleration is just the rate of change of the angular speed. And so we see that we go from 0 to 20 in 5 seconds. So our acceleration will just be 20 divided by 5. So that's the change in angular velocity over the time. It'll be 4 radians per second squared. Then we need to determine the moment of inertia of the system. And well, we know that the net torque, so torque net, is equal to the moment of inertia times the angular acceleration. Again, very similar to the F net equals to ma, Newton's second law in the mechanics portion of the syllabus. And well, we know the net torque as we just calculated this, and we also know the acceleration, so the moment of inertia will just be the torque divided by the acceleration. So that will be 33 divided by 4, which is 8.25 kilogram meter squared. It's important that here we have to take the net torque. So in this formula, same as in mechanics, we always have a net force here, not just some random torque or force. Always has to be the net torque. And then we are told that once it reaches its maximum speed, the two forces are removed, and the spheres now move to the outside, away from the axis, outline why the angular speed decreases when this happens. And well, we need to consider how the moment of inertia of this system is going to change. So we know that moment of inertia is mass times the radius, well, no, moment of inertia is the sum of mass times the radius squared. So we take some point mass, we look at the distance from the axis, we square that, and we multiply it by the mass of the point mass. So here we see that for both balls the radius is increasing. So the distance from the axis has increased from here to here. So the moment of inertia of the whole system is going to increase. So moment of inertia of system increases. And well, we also know that angular momentum must be conserved, as that is always conserved. Momentum is conserved. So this is like linear momentum in mechanics, always conserved in a closed system like this. And well, when we have no forces acting or anything, obviously. And well, we know that angular momentum is just the moment of inertia times the angular speed, and we see that the angular momentum is constant, so if the moment of inertia increases, then our angular speed must decrease. So that when we multiply them together, we still get the same number. So that is why it's going to decrease. So it will slow down a little bit. And then we need to show that the rotational kinetic energy is this 1/2 times the angular momentum times the angular speed. And well, it's rather straightforward. We know that the kinetic energy is just 1/2 moment of inertia times angular speed squared. And well, we can almost see angular momentum in here, as we can write this angular speed squared as just omega times omega. And then we see that this over here is the angular momentum. So that's about it. Like this. Then when the spheres move outward, the angular speed decreases from 20 to 12. Calculate the percentage change in rotational kinetic energy. All right, so what we need to calculate is this change in kinetic energy from the initial phase, which can be like the first one, and the second phase when we have moved the spheres outward, that will be kinetic 2. And well, we have just given found this expression for rotational kinetic energy. Usually in IB, whenever there's a show in front of the question, so we need to show something, then that's always suggesting that this result we have shown here, we're going to have to use somewhere later on. So this is like always the case 99% of the times. And so if we notice that, instead of writing that the kinetic energy is this 1/2 moment of inertia times angular speed squared, instead we can write 1/2 times the angular speed times the omega, just omega 1. And same for the bottom. And well, we see that the 1/2s cancel out. And we also see that the angular momentums cancel out, right? Because we have just said that these two must be constant. So the angular momentum is not changed, it's always conserved here. That's what we said here. So this just simplifies to omega 1 over omega 2. And then, well, this will just be approximately a 40% energy loss. So like 20 over 12. So that's a 40% loss. Like this. Yes. And well, if you would want to calculate with this formula, then you would have to make sure that the moment of inertia here is different when the spheres have moved to the outside. And well, we don't really know exactly how much is changed by, so we couldn't even use that really. And just stating that the moment of inertia for both situations is the same and then just canceling them would be incorrect for us to assume. So we have to use this formula. As if we would know by how much they move to the outside, maybe we could solve it, but even then I'm not 100% sure, as we don't really have enough information in the question to be able to calculate the new moment of inertia. And then we need to outline why, one reason why this is unrealistic. Well, maybe air resistance is not taken into account. Air resistance is neglected. We could also say that for a real person, for a real dancer, the mass isn't distributed evenly throughout their bodies, but here we just assume that all of the mass is uniformly distributed within these cylinders and stuff. And well, yeah, I mean, it's also not very accurate to model a person with just like rods and balls for their hands. So you could also say something like that. So we can also say, for a person, mass is not distributed equally. And well, then this was this question. I hope I was able to help your understanding, and see you in the next question.